So in today's video we're going to look at section 1.1, which is coordinate systems and graphs. A good way to display numerical data in a visual way is by using this Cartesian coordinate system on the xy plane. So we know that it looks something like this, with an x-axis being the horizontal axis and the y-axis being the vertical axis. We do this by constructing an arbitrary point, which is the origin here, which is 0 units across on the x-axis and 0 units up on the y-axis. So it's where the x and the y-axis cross. And then in order to plot our data points, we see how many units they are across on the x-axis and how many units they are up on the y-axis. So, for example, any data point should have the form xy, where the x part of the data point comes first, the y part of the data point comes second. So for example, 3, 2, okay, means that we are 3 units across from the origin on the x-axis and 2 units up from the origin on the y-axis. So if I plot out a few units on each axis, this will be done for you obviously on your homeworks and stuff so that you can see it more clearly. But 3, 2 would be 3 units across, so 1, 2, 3 units across on the x-axis and 2 units up on the y-axis. So that would mean that our point 3, 2 would be right here. The x and the y coordinates can be positive, negative, or 0. Okay? So whenever you plot these points, please keep in mind that your x coordinate is always first, your y coordinate is always second. So deal with the x coordinate first and then see whether you go up or down on the y axis. Let's try another point. Let's try negative 2, negative 1. So negative 2, negative 1 has both a negative x and a negative y coordinate. So we go negative 2 across on the x-axis, so I'm going 2 units to the left on the x-axis and 1 unit down on the y-axis. So I go negative 2, which is 2 units to the left on the x-axis, and then 1 unit down on the y-axis. So my point negative 2, negative 1 would be there. Let's try another point. Let's try negative 3, 0. Okay. In this case, I have a negative x coordinate but a 0 y coordinate. That tells me that I am going to be on the x-axis because I am not shifting away from the origin in the y direction. I'm still at 0 for my y coordinate. So negative 3, 0 should be negative 3 in the x direction. So I'm going 3 units to the left in the x direction. And then because I have a 0 y component, I'm staying on that x-axis. I don't shift up or down. So negative 3, 0 actually ends up lying on the x-axis. On the other hand, if I had the point 0, 3, this time I have a 0x component, so I stay at this point on the y-axis because I know that x is going to be 0 for that particular data point. So I start off at x is 0 and then I go up 3 units in the y direction. So that means that the point 0, 3 actually ends up lying on the y-axis 3 units up from the origin. We can also graph equations, okay? So at this point, we're just plotting out points. What you can do is you can actually graph a whole equation. So it means that every point that lies on that curve satisfies an equation. So every xy pair is going to satisfy x and y in my equation, okay? So let's do an example to show this. Are the points... I'm going to do 3, 7 and 4, 5 on the graph of the equation y is equal to 5x minus 8. Okay, so to see whether, if I actually drew out this line, this would actually end up being a line, it's a linear function. If I were to actually draw this line, y is equal to 5x minus 8, if I then plug these points in, so if I plug in x is equal to 3 and y is equal to 7, and this equation is satisfied, it tells me that that point would lie on the line on that xy plane. Okay, so let's start with 3, 7. If I plug in x is equal to 3 and y is equal to 7, that would mean that my equation would look like this. So my left-hand side is 7, and my right-hand side, when I multiply this out, I would have 5 times 3 is 15, minus 8, which we find is also equal to 7. So for this particular point, my left-hand side equals my right-hand side, and therefore it tells me that this point satisfies the equation, meaning that that point is on the line. So 3, 7 is on the line y is equal to 5x minus 8. How about the point 4, 5? We're now going to plug in x is equal to 4, y is equal to 5. So if I plug in x is equal to 4 and y is equal to 5, my left-hand side would be 5, and my right-hand side would be 5 times 4 minus 8. So my left-hand side is still 5, my right-hand side is 5 times 4 is 20, minus 8, which gives me 12. Well, 5 doesn't equal 12. That tells me that at this particular point, I do not satisfy this equation. So this point 4, 5 does not lie on the line. Okay, as the equation is not satisfied for x is equal to 4 and y is equal to 5. This particular equation, y is equal to 5x minus 8, that is what is called the slope-intercept form of the line. We'll talk more about this as we go on, but it's the traditional form that we see a line presented in. Okay? Sometimes it may be presented in a slightly different way, being the general form of a line, and we'll come to this in a minute. But the general form of a line is normally something times x plus something times y is equal to a constant. So same deal as what we have done here, except this time I'm going to plug it into a particular point into a line that is put in general form and not the slope-intercept form. It's going to work in exactly the same way where I plug in x and I plug in y and I see if the equation is satisfied. It's just going to look slightly different when we plug it in. So is for negative 7 on the graph of the linear equation 2x minus 3y is equal to 1. So you can see that this particular equation looks slightly different to our last one. Okay, on the last equation we have y on the left hand side and then something times x plus a constant on my right hand side. This time in the equation, I've got something times x and something times y on the left-hand side and a constant on the right-hand side. Exactly the same as before. You're going to plug in the x-coordinate and the y-coordinate if it's satisfied, therefore this particular point is on the line. So 2 multiplied by 4 minus 3 multiplied by negative 7. We want that to equal 1. Okay, so I've plugged in my x, plugged in my y, so I get 8. Then negative 3 times negative 7 is 21. And then 8 plus 21 is 29. Well, that doesn't equal my right-hand side of 1. Therefore, this point is not on the line 2x minus 3y equals 1. So no matter what form the equation comes in, you could still plug in x and y like before, and you should see whether the left-hand side equals the right-hand side for the equation at that point. If it does, then it means that that point is on the line. If not, it means that the point is not on that line. You should see from both of these equations, they are actually linear equations. So a linear equation is just an equation that when you graph it, it is a straight line. So a linear equation is an equation whose graph is a straight line. Okay. I'll give you a quick example for this. If you have done a lot of graphing equations before, you would be able to easily graph this, but we will go through that. An example would be y is equal to negative 2x plus 6. If you were to plot this out, plot out a few units, you'll see that this particular graph actually goes through 0, 6 and 3, 0. And then you can join those 2 points together. We will be going through more of this as we do this course, but I am going to plot this line very quickly so that you can see. Okay, but that's roughly what this graph would look like. Whenever you do any kind of graphs or anything for this course, you do not have to be accurate in your sketches. For the online homeworks, it will help you draw this line. But when you're sketching anything, feel free to just give me the points that it will go through and then join them up exactly like I have here. Now we notice here we have this constant 6 that is at the end of this equation. That, if you've done some of this stuff before with graphing lines, you'll know that that is called the y-intercept, and we'll go into more of this later. But if that constant ends up being 0, so let me write out the equation where this constant would be 0, which would be y is equal to negative 2x, so slightly different equation. Instead of going through these two particular points on the x and the y axis, it would instead go through the origin, because the origin satisfies this equation. You'll notice this if we set x equal to 0 and y equal to 0, the left and the right hand sides of the equation are equal. So 0, 0, the origin, satisfies this equation, which means that 0, 0 is on the line for that equation. So this line, y is equal to negative 2x, would go through the origin. As we go through this, and as I said, this line will go through 0, 0, and the line y is equal to negative 2x plus 6 goes through the points 0, 6 and 3, 0. Those are the points that this line goes through that are on the x and the y axes. Okay, those are called the intercepts of a line. So the intercepts of a line, they are the points where a particular line crosses the x and the y axes. Okay, so the point where it crosses the x-axis is called the x-intercept. So where it crosses the x-axis is the x-intercept, and it will be of the form a0. So it will be some constant for our x coordinate and then 0 for our y coordinate. Okay, and that would be the point that it crosses the x-axis, because if we go back to here, okay, you'll notice the x-intercept for this equation has a particular constant for the x coordinate. So in this case it was 3, because it's 3 units across from the origin on the x-axis, but because it is on the x-axis, it has a 0 y component. So whenever you get an x-intercept, the point at which a line crosses the x-axis, it is always going to be of the form a0, where a is some constant. Where it crosses the y-axis is obviously the y-intercept. Now this time, the y-intercept will be of the form 0 with some constant b as our y-coordinate. Go back to our original example. Okay, 0, 6 was the y-intercept of this particular equation because it has a 0x component as it lies on the y-axis, and it has 6 as its y-coordinate because it is 6 units up from the origin on the y-axis. So a y-intercept is always of the form 0 and some constant b for our y-coordinate. How do we find these for a particular line? So let's say I am given this equation. Okay, y is equal to negative 2x plus 6. Okay, if I'm given that equation, how do I find that my x-intercept is 3, 0 and my y-intercept is 0, 6? If I'm trying to find the x-intercept, okay, to find the x-intercept, all I'm going to do is set my y equal to 0. Why do I do this? Okay, go back to this example. To find my x-intercept, I'm going to set y equal to 0. Okay, the reason I do that is because I know that my x-intercept is of the form some constant for x, a, okay, we're going to call it a for now, some constant a, and then 0 for my y component. We know that the y coordinate is 0 for my x-intercept, okay? So if I set y is equal to 0, I know that to be true, so I'll set y is equal to 0, and I then solve my equation for x. Then that will give me the x component, my x coordinate, for this particular x-intercept. So all I do to find an x-intercept is I set y is equal to 0 because I know that to be true for an x-intercept of a line, and then I solve for x. Okay. To find the y-intercept, I'm going to set x equal to 0 and solve for y. Why do I do that? Exactly the same theory as I did for the x-intercept. For my y-intercept, I know that x is equal to 0 for a y-intercept, okay, because I know it lies on the y-axis. Anywhere on the y-axis has a 0x component, okay? The x-coordinate is 0. I then just need to find the y-coordinate. So if I set x is equal to 0 and solve for y, that will give me that constant b that we looked at here, okay? If I solve for y, it will give me that constant b, and therefore I will find my y-intercept. Okay. So let's do that for our example. So in our example, we had y is equal to negative 2x plus 6. So find the intercepts for y is equal to negative 2x plus 6. Okay. For the x-intercept, okay, I need to set y is equal to 0 and solve for x. So if I set y is equal to 0, my left-hand side equals 0, and I have negative 2x plus 6. I need to solve for x. Okay. To make everything positive, I'm going to take this term onto the other side. So I'm going to add 2x to both sides. Okay, that gives me 2x on my left-hand side, and then negative 2x and positive 2x cancel out, and I get 6 on my right-hand side. Divide both sides by 2, and I get x is equal to 3. So that tells me that my x-intercept has 3 as the x-coordinate, and we know that the y-coordinate of an x-intercept is 0. So 3, 0 is my x-intercept. How about my y-intercept? My y-intercept, I'm going to set x equal to 0. And I'm going to solve for y. Okay? So if I set x equal to 0, I get y is equal to negative 2 multiplied by 0 plus 6. Negative 2 times 0 is 0. Plus 6, which gives me 6. So y is equal to 6. That tells me that my y-intercept, okay, we know has an x component 0, so my x coordinate is 0 and my y coordinate is 6, and that's my y-intercept. And that agrees with what I have for my graph of y is equal to negative 2x plus 6. There are a few linear equations that I want you to keep in mind. First one that I want you to think about is x is equal to some constant a. Okay. An example of this would be x equals 3. Any linear equation of this form has a completely vertical graph, okay? It's a vertical line that will go through the x-axis at 3, 0. So it goes through the x-axis where x is equal to 3. So it would look something like, if I graph this out, let's give myself some units on the x-axis. Again, only has to be a sketch. But if I were to draw this out, it would look something like this, where it goes through 3, 0 on the x-axis. So any graph of an equation of the form x is equal to a is just a vertical line through this particular point on the x-axis, being in this case 3, 0 or a 0 for any constant a. Why is that? Any point on that line has an x-coordinate of 3. Okay? Any point along that line, so if I were to take another point, let's say here, that point still has an x-coordinate of 3. So it still satisfies the equation x is equal to 3. The y-coordinate of any point doesn't matter. Okay? It doesn't matter whatsoever, because this equation is not affected by the y-coordinate. It is only affected by the x-coordinate being 3. So the y-coordinate can be whatever it likes. That's why it is an infinite line that runs through that particular point. In this case, x is equal to 3. Okay? So it runs through 3, 0. But it can have any y-coordinate that it likes. So it's just going to be that vertical line that runs through that point 3, 0 on the x-axis. Okay? In a similar way, let's look at graph of the line form y is equal to some constant b. So b is a constant. What does that look like? Well, in the same way that we had with our x is equal to a example, okay, we said that every point on that line satisfied, in our case, in our example, it was x is equal to 3. Well, in this case, every single point on this line has to satisfy y is equal to the constant b. So let's do, in this case, y is equal to 3. Every single point on that line must satisfy y equals 3. The x-coordinate doesn't matter. It can be whatever it likes. That means that our line, let me do a couple points here. Our line must go through 0, 3. Okay, it must go through 0, 3 on the y-axis. Now, I can pick any point on that line. Let's say I pick this point here. Okay? Doesn't matter what the x-coordinate is. My y-coordinate is still 3, so it still satisfies my equation. Same as every point along that line. That means that my line is going to be a horizontal line that runs through that point 0b. In this case, it's 0, 3. Okay? Because no matter what the x-coordinate is, my y-coordinate for any point on that line is always 3. How about y is equal to mx, where m is a constant? Okay. We looked at this very quickly before, where we did y is equal to negative 2x, and we said it went through the origin. So this line will always go through the origin. Okay, it will always go through 0, 0. That's because regardless of what m is, 0, 0 is always satisfied. So x is equal to 0, y is equal to 0 means that my left and right hand sides of my equation are always the same. Okay, so this equation is always satisfied by the point 0, 0, which means it must lie on the line. So if I look at the graph of y is equal to 3x, okay, I know that this particular line must go through 0, 0, because when x is 0, y is 0. So I know that it has to go through 0, 0. Now, doing a quick sketch here, what you would normally do is figure out another point on the line, join them up, and then you can extend the line in both directions. Another point on this line, if you were to plot it out, would be, for example, 5, 15. When x is 5, y is 15, okay? You can join those two up and then extend the line in both directions. And that would be the graph of the line y is equal to 3x. Okay, as I said, it only has to be a sketch. You do not have to do this accurately, but convention is that you plot out 2 points on a line and then join them up and extend them in both directions, and that will give you enough of a sketch of a line. Another type of equation that we have to be aware of, which is the most common type of equation, is y is equal to mx plus b. Okay, these lines don't go through the origin unless b is 0, but these lines tend to have an x and a y intercept unless b is 0. So very similar to our previous example that we had. Let's look at this one. Y is equal to negative 2x plus 6. I had a particular intercept on the x-axis, I had an intercept on the y-axis. I join those two up, and then I can extend that line in both directions. So these lines always have both an x and a y intercept. So we saw for x is equal to a, we just had an x intercept. For y is equal to b, we just had a y-intercept. For x is equal to mx, we had that it went through the origin. So that was both our x and y-intercept. And for y is equal to mx plus b, where both m and b are constants. Okay. And b doesn't equal 0. Separate x and y intercept. Okay. They are the main types of line that you will see. As I said before, this particular form, which we will look at in section 1.2, is called the slope-intercept form of the line. And if you've done anything with graphing equations before, you will know why, but we will go through that in section 1.2. So this is called the slope-intercept form of the line, and it is the most common form that you will see linear equations put in. Another type, which we did look at the start, is called the general form of a linear equation. So any equation whose graph is a straight line can be written as the general form of a linear equation. Okay. And the general form of a linear equation looks like cx plus dy is equal to e, where c, d, and e are constants. Okay, and obviously x and y depend on what points you have on the line. Another point to note here, both c and d aren't both 0 at the same time. So c and d are not both 0. Okay. Otherwise, you would end up with a situation where you would have some random constant e would equal 0, and obviously that does not make sense. So, quick example of something that may occur is where you will have to write the general form of an equation in that slope-intercept form. So you may be given a particular equation for this linear equation being of the form cx plus dy is equal to e. You may then have to write that in slope-intercept form, y is equal to mx plus b. So you're going to have to rearrange this to look like the slope-intercept form. We'll go through an example of that so you can see how it's done. This is kind of a quick algebra recap. So write the equation (4x plus 2y equals 6) in slope-intercept form. And then we're going to go a step further. We're going to find any intercepts of this particular line. So we're going to find any x and y intercepts. And we're also going to do a quick sketch of the graph. So find any intercepts and sketch the graph. So first thing we're going to do is to put this in slope-intercept form. So I've started out with 4x plus 2y is equal to 6. Okay, I've got to rearrange this so that it has to look like y is equal to mx plus b, where m and b are constants. Okay. Ideally, what I want to do here is leave any y terms on the left-hand side and get all my x terms on the right-hand side, and then I can rearrange the constants. So I'm going to get that 4x over to my right-hand side. So I'm going to subtract 4x from both sides. That will leave me with 2y on my left-hand side, and then I'm going to have negative 4x plus 6 on my right-hand side. Okay, you can do it as 6 minus 4x, but remember we want it in the form y is equal to mx plus b. So I really want my x term to be at the front. Then my left-hand side is fine, except for I have this coefficient of 2 in front of the y, which I would really like to get rid of because I want it in the form y is equal to something. So if I divide both sides by 2, I end up with that result. So if I divide both sides by 2, my left-hand side becomes y, and then I've got to divide every single term on my right-hand side by 2. Remember to do this with every term, not just the x term. So I've got to divide negative 4x by 2. I also have to divide 6 by 2. Make sure you do this. This is a very common mistake that people make. They do not divide every single term in that equation by that number. So if I divide both negative 4x and 6 by 2, I'm going to get negative 2x, and then 6 divided by 2 is 3. So this is my slope-intercept form of my line. So it's exactly the same linear equation, it's just put in 2 separate forms, okay? So these both represent the same line, it's just that they are written in different forms. We tend to prefer this particular form just because, as you'll see in section 1.2, it actually makes it a lot easier to see what is happening with our graph. Okay, the next thing that the question asks is to find the x and the y intercepts. So to find the x-intercept, I set y equal to 0 and solve for x. So for my x-intercept, okay, I'm going to set y equal to 0 and solve for x. Okay, so if I set y is equal to 0, you can do this for either form of our line. So I can do this in the general form, or I can do this for the slope-intercept form. Completely up to you which way you want to do it. Okay. I'm going to do this for the slope-intercept form just to kind of keep it consistent with what's going to happen with the rest of this chapter, but feel free to plug in y is equal to 0 into this equation here. You're still going to get your same answer for x regardless of which one you put it into. It's totally fine. I'm actually going to put it into this one just to keep it consistent with what we're going to be doing in future chapters. So if I plug in y is equal to 0 into that, I'm going to get 0 is equal to negative 2x plus 3. Subtract 3 from both sides, or add 2x to both sides, completely up to you. I'll actually add 2x to both sides to make everything positive. So if I add 2x to both sides, I'm going to get 2x is equal to 3. Divide 3 by 2. I get x is equal to 3 over 2. Okay, so my x-intercept is 3 over 2 for x and 0 for my y component. For the y-intercept, I set x equal to 0 and solve for y. As I said, you can plug x is equal to 0 into either form of this line. You'll still get the same value for y, but to keep it consistent with the rest of this chapter, I'm going to do it for this particular slope-intercept form down here. So I'm going to set x equal to 0 and solve for y. If I do that, I'm going to get y is equal to negative 2 times 0 plus 3. Negative 2 times 0 is 0. And 0 plus 3 is 3. So my x-coordinate is 0, my y-coordinate is 3. So I have my x-intercept and my y-intercept. Now I want to sketch the graph. So to sketch the graph, I'm going to plot out my intercepts, and then I can join them up and extend the line. So if I do that, we'll sketch a quick x and y axis. Okay, and I'll plot out some units on here. Okay, then I know it goes through 3 over 2, 0. So that would be 1.5 is 3 over 2. So that would be, here is my x-intercept. So that's 3 over 2, 0. And then my y-intercept was 0, 3, which is up here. Okay. Then I can join these up and extend the line, and that would be a sketch for my particular linear equation. So that would be my graph. So this is y is equal to negative 2x plus 3. And that's a quick sketch of it. Okay. If you go to the textbook, example 5 on page 4 is actually a good real-world example of this. So I highly encourage you to go through that. It's example 5 on page 4, and it gives you this real-world example of doing things like this. They will also come up in homeworks as well. So I highly encourage you to go ahead and look at that as an extra example. But we will come across a lot more of this as we go through the rest of this chapter. So please make sure that you are comfortable with this before we carry on.